Welcome everyone to the 21st session of Statistical Learning in Practice. I shall now finish the theory bit of time series from the last lecture, so just a couple more models, and we'll then continue with the practical, which is a bit of a it's a bit more illustrative than other practicals. We're not really doing estimation perhaps until the very end, because estimation and inference will occupy us in the next practical. So for time series, we need to introduce the ways in which we're going to do this, and that I will do in the next theory lecture. So the theory lecture on Friday, there is a chance I'll have to record it. And then Monday, I will. I will do this live as usual. So that's on Monday next week, and then on Wednesday we'll have this session in which you can ask questions about the course, and therefore I will cancel the office hour of that Wednesday. If because you're in a time zone that you cannot attend lectures in the morning and you still have questions, just drop me an email. Yeah. Okay. So very briefly, we were missing, so we ended the lecture in moving average models. And so we covered, sort of stationary time series, and that included autoregressive, moving average, and then we can put them together now to have AMA models, which is autoregressive moving average models. So 3, 1, 3, 3, 1, 3. So autoregressive, moving average, so AMA models. Okay, so definition 27. We have that X, so time series follows an AMA model of orders P and Q. If it is stationary, so this comes from the autoregressive definition, so we need to put them together. If it is stationary and satisfies that X at time t can be written in terms of its previous values, regressed with some parameters, so just the usual AR expression. So we have P of them, and then we also add the MA bit. So for this we need theta 1, t minus 1, so on up to theta q, epsilon t minus q, and this is for all t in our, I think we're defining things on z, but otherwise, if I was in the last lecture doing it for t, capital T, then just write capital T. And this is for some phi 1 to phi p, theta 1 to theta q in the reals, and we need that the phi p, phi q, and theta q are distinct from 0, because otherwise they would have, or this process would have a lower order. And this is also for some white noise, for some sigma squared, that in the definition we assumed that it is strictly positive and finite. So that's something we obviously assume when we say that epsilon follows this process. And then an additional condition that we need and this is particular to ARMA and not really from AR or MA, is that without loss of generality, what we are going to assume is that this AR operator and the MA operator have no common roots. Okay, so if they did, then we simplify them, and then we take the resulting. So I mean, think that you can take all of these guys to the left, okay, and then that would give you this capital phi operator, and then on the right hand side you would have the capital theta operator. So if they have common roots, then treat them as polynomials, cancel whatever needs canceling, and then with the remaining polynomials, rearrange the expression so that you get yet another ARMA process that actually should be the same. And therefore, that is what we are assuming in the definition, okay? Okay, so they have no common roots. So that's the end of the definition. And so a little remark is the following. So definitions 23 and 25, which correspond to causality and invertibility in AR and MA processes, respectively, and also propositions 3, 4, and 5. So these apply to ARMA models. Without modifications, yeah. So the same conditions apply basically to ARMA models if you want to talk about causality or invertibility. Okay, so that's for ARMA models, and now we have So I said I would focus on stationary processes, but we can introduce a model for non-stationary processes that is very related to ARMA models. And so we do that rather than going to, generally non-stationary processes. So we focus on, so the only instance of non-stationarity is this model that I'm going to introduce. So this is autoregressive iterated, so that's the difference now, this is the new word, iterated moving average this is ARIMA models. Okay, and so what's the idea behind these models? Well, so remember from the last theory lecture that the random walk, this guy, is not stationary. Okay, so it's not stationary. So this corresponds to the AR1 relationship, but we said that it's not possible to have stationarity. So we showed how to argue that. And so this is not stationary, but yt equal to xt minus 1 is. Okay. Because of course, the difference between these two is the epsilon t, right? There's the white noise, so you cannot get more stationary, so to say. I mean, that's there's not really a degree of stationarity, but you understand what I mean. And so what we see is that we can introduce So we let delta be 1 minus b, and this is going to be called the differentiation operator. So and this, if you like, this, its powers. So this idea of differentiating or differentiating the time series by taking the differences is actually one that applies to many other processes, not just a random walk. And then what you can do is that if you difference, if you take the differences repeatedly, so r times, for instance, then you may get a stationary process, and actually that's the case, that it applies quite generally, and so this is a useful model in that respect. So definition 28. X follows an ARIMA model of orders P, D, and Q. Okay, so I wrote R, but D is more, well, it's different things. So of those orders, if we have that, if we take the differences D times of our XT, then it follows an ARMA model of orders P and Q. Okay. So by the way, if we talk about the phi's and the theta's and the operator AR and MA operator of an ARIMA model or time series, then we are referring to those of the differenced time series, not really of the original time series, but rather of the one that follows now, the ARMA model. Yeah. Okay. So that's enough for the theory. If there are any questions, shout out. Otherwise, I will go to the practical, for which there should be solutions online already.
Just a quick thing. I think the title might be wrong. Isn't the I in ARIMA for integrated rather than iterated?
Did I say iterated? I'm sorry. Yes, integrated. Totally. Thank you.
Also, well, I guess we'll come to this in the practical. I'll ask about it later. I'm interested to know how they initialize the function itself, the ARIMA. Yeah. Cool. Thanks.
Okay. Thank you.
Yeah, excuse me. I have a question.
Yeah.
Why do we, for the ARIMA, why do we restrict to powers of delta, not more general polynomials of B, as we did for ARMA?
Polynomials of order D, you say?
No, like for the moving average, for instance, we use just polynomials of B general, and there for the ARIMA we just take powers of D. Why do we restrict to powers of D for the ARIMA?
I mean, I don't see the similarity between MA and the powers of the differentiation operator. So they're different things, right?
Yeah, totally. But
so
yeah.
Can you reformulate the question, please?
Yeah. We want for X to be an ARIMA, we want to have a specific the operator D at the operator delta for the power D.
Okay.
And why this operator specifically?
Right. Okay. I mean, they really are fundamentally different things in that you can have a polynomial model for your MA operator, and then you will be able to estimate the parameters of that polynomial. But for differentiating a time series, that's a bit different. You're not really placing weights and trying to estimate that. So that would be actually quite hard to do. But rather, I mean, I think the idea is just this, I'm not saying it's not possible to have a model with, a general polynomial for delta, as you're saying, but integrated ARMA models are just that, right? So you're just integrating the series again and again. So that's what the model is about. It's just integrating. It's doing the opposite of differentiating. So that's what the integrated ARMA models do. You could have a more general, of course. I mean, no one stops you from doing different operation on the XT. But then that wouldn't be an ARIMA model. And there are ways to try to find this order of an ARIMA model. But now if you come out of this setting where you're just taking the differences, then you will have to really build new methodologies for not only finding the order, but also, whatever values of the coefficients that will go in the delta polynomial, how to estimate those. And that, I don't think that's a very simple endeavor, but you're not, no one stops you from doing that, really.
Okay.
Yeah. And I think, again, models should be simple. Yeah, they should be, you should have a good reason to believe that, you by taking a very peculiar transformation of the XTs, then you will get a stationarity. While this is a bit more intuitive, right? Taking the differences is actually something that is sort of is intuitive in some sense, right? Okay, so let me, okay, now I need to stop sharing. Well, is there a question in the chat? Yeah, thank you, Lenny. So stop share, and then, okay. So if you have any questions, just fire off.
Hi, Alberto. I have a question about the AR processes.
Mm-hmm.
In the ACF plot, why is there a bump?
A bump?
Like, a bump where it sort of goes down and comes back up. Is that just a random effect?
So you mean this sort of switching from positive to negative here?
In the next one along with the AR processes.
Sorry. Yep. Okay.
Yeah, there is a slight bump there. I guess that is just a random effect, or is there something more?
Yeah, that's from the data. Yes.
Okay.
Yeah, it doesn't. When you have finite data, you will never get exactly the functional dependence you would get, from the theory. I don't know whether there is. I forget if it is in the example sheet or in the exam from last year that there is a condition that the autocovariance function, autocorrelation function, satisfies if it is the sample version. And so it means that basically you're not unrestricted in some way. You have a restriction to satisfy when you are the sample autocorrelation function, which then necessarily violates the theoretical autocorrelation function unless you are under asymptotics. So finite samples, you will never get exactly what the shapes that you will be getting in the population autocorrelation functions.
That's interesting. Cool. Thank you.
Yeah, no problem.
Hi. When we looked at the MA1 process, you say in the solutions that the sample autocorrelation function shows lag1 correlation. I think this is on page 81. Yeah, and we can see that maybe the vertical line at lag1 is a fair bit above the upper blue dotted line at 0.2. Is that what to show lag1 correlation is?
So, I mean, I presume you have in mind what these blue dots are?
Yes.
Okay. So that, I mean, yeah, so just to remind everyone, that comes from the beginning of the practical, in which we have that thanks to the central limit theorem, we can have a confidence interval for each of them. So this is not a simultaneous confidence band, but rather you should be looking at it individually. And it is a 95% confidence level interval for each of them. And it corresponds to the null model of having a white noise. So, if you begin the experiment by saying, well, I wish to see whether the lag1 autocorrelation does not correspond to the lag1 of a white noise, then you can test that this way. And what this would be telling you is basically that this is significantly beyond what one would expect under a white noise, and so there is statistical evidence to think that the lag1 correlation is not zero, and therefore at least looking at the rest of the values, then you sort of make a guess, an educated guess, thinking that this can be an MA1 process. I don't know if that's if that answers the question.
Yes, I think so. But then that makes me think, if we go back to the very first time you computed an ACF lag plot, when we were considering it was the AR1 model. Again, the lag1 line is now below the lower confidence interval. Yep. So is that for this? Do you say that does that mean we can derive the order of that process in exactly the same way?
So, okay, so to begin with, I mean, this is not this should be understood with care, or it should be interpreted with care because of this pointwise confidence interval interpretation rather than a band. And so I think, generally speaking, one just tries to get an idea of whether this is corresponding to one time series or a different one, essentially. So you could be deceived by this. Yes, you could be deceived by this. And I guess if you if you then look at this, then there is a slight difference in that it seems that these are on one side and then these are on a different side, while this one seems a lot more random, so to say. And so this is what would make you think, suspect that maybe this is not, an MA process or, an MA process. But if basically what is happening is that you're worried about seeing these without seeing anything else and seeing these and not being able to distinguish between the two, then I agree with you, basically.
Thank you. That definitely, I suppose, with your response, it makes me think my actual question was sort of, how much is that sort of plot useful in deciding the order? And I've got a better idea. So thanks.
Yeah, I mean, this is finite data, so the interpretation of any, you could build a test here, right? You could build a test that tells you, well, if it comes out of the confidence interval, then I reject the null hypothesis of having a white noise, and so that is a frequentist test. And so what you would have to do is to have multiple samples of white noises, and then you would see that indeed 95% of the cases, if you have a white noise, then you would be inside. But for one single experiment, it is one diagnostic tool, just as we had diagnostic tools in the linear model, but they're not a white or black type of. They don't give you white black answers, right?
That makes sense.
Yeah.
Could I firstly ask a little curveball question?
Mm-hmm.
Which is, I'd be quite interested to see some proofs of some of the results about like the unit root condition and things like that. I had a little look at the Brockwell book.
Mm-hmm.
Is the other reference going to be good, or like where should I go to kind of dig these things out a bit more?
I mean, that's a classical one. I forget now whether it is there or not. Is it not there then?
It seemed all like.
I mean,
it didn't seem to give many proofs, I thought.
Is there no annex in it or like appendix to it?
There are some appendices. I haven't gone through them, so maybe I can have another look.
Yeah, because it's true that in this field, more like time series or econometrics, the proofs are a bit. Sometimes they just hide them.
It feels like there's some quite nice maths going on underneath.
Well, I mean, it's central limit theorem, generally speaking, for these things. The unit root maybe not exactly as simple as that, but if you don't find it, then I'll dig out a different reference.
Okay, thank you.
Sure.
And then I don't know. Would it be worth going through the practical kind of slowly-ish at this point?
Is it?
I don't think I've got any like massive questions. I've just got like a couple of little ones scattered throughout, sort of thing.
Yeah, I mean, feel free to ask, because I think given that we've already set a tone in the practicals in which basically is driven by questions, then I think I will just leave it like that. Because I mean, after all, you've had the solutions and everything now for a bit. So feel free to ask, yes.
I think probably we've already discussed this a bit when we talked about the initialization of Y1. So I'm sorry to go back to something again. It was just when we had the previous theory lecture, when we talked about stationarity, I didn't immediately pick up that we would need the variances to always be the same. I knew we need the means to be the same. I suppose, was that obvious? Did I just miss something really obvious, or actually is it a bit more of a derivation?
I think I think it is not explicitly stated, but it's simply an implication of the definition. So if you have finite, so if we focus on weak stationarity, I mean, if we have strong stationarity, then strong stationarity doesn't mean that you have finite variances. But if you assume finite variance in strong stationarity, then certainly, the distribution of each element should be the same, right? Because time shifts, right? They keep the distributions or the joint distributions, and so if you have just one element, then you're saying that you keep the distribution. And then we said that we would try to keep the same type of properties for the first and second moment by introducing the weak stationarity. And so in weak stationarity, we have that, the second condition is that we have finite variance. And if we have finite variance, we can define the autocovariance function. And then the autocovariance function, the assumption on it is that it only depends on the lag. So it means that, if you plug in TT rather than TS, so if you take S to be T, then the lag is 0 for any T.
Oh, sorry. Yes, no. So it is obvious. You're being very polite. You could just say, yeah, that makes sense now. Thank you.
Because there is
plugging in TT.
Okay. Yeah, and there is. I mean, it can. I just wanted to be minimalistic in the assumptions, so not to repeat what one bit of an assumption gives you, basically.
Yeah, that makes sense. Thank you.
Could I quickly ask about initialization?
Yeah.
So you make the point in the practical that our kind of original function, where we are kind of naive and we don't kind of correctly scale the variance of the first point, isn't like a valid stationary time series because our initial variances are just a little bit too low. So presumably the ARIMA function does this correct initialization variance sort of thing.
What ARIMA function are you?
Just the arima.sim kind of built-in function, which we use later on.
Presumably, yes.
And then,
yes.
So if we're doing some sort of integrated process, it feels like we need some sort of initial condition on the first difference. Do we just take that to be 0?
I mean,
I guess I could probably check.
Yeah, I mean, you could do that, yes, but I guess the conditions go on the integrated, not on the integrated, excuse me, on the difference series, right? That gives you the ARMA model, and then it's a matter of reconstructing, now the integrated process, and for that, indeed. Yeah, I don't know
I've just checked the plot actually and realized, it does start from 0.
Yeah, exactly.
So that must just be a reasonable default in that.
Exactly, that would be a reasonable default, because after all, if it doesn't, if what you want model doesn't start at 0, then it's just a matter of shifting it.
Yeah.
So that's the baseline, I guess.
Another little thing.
Yeah.
Oh yeah. So the next little thing is, so in the section kind of late on before the real data, when we're looking at this ARIMA process. I noticed that the kind of ACF plot that we get when we look at the kind of corresponding ARMA process has some it seems to have some oscillatory behavior. That doesn't seem particularly random. It seems like there's some trend.
Could it be this?
Not talk about it too much.
Do you mean the one in 83, or do you mean the one for the ARIMA itself? So before or after differentiating?
I think page 80. Yeah, 83.
Okay. Yeah. So there's this. Yeah. Yeah. So the question is,
The question is why slash, well, I guess maybe this is something I can think about as well, but.
Sorry, I don't think you asked the question.
So the question is like, why is there this nice trend or some sort of oscillating extra behavior?
So firstly, the autocovariance functions or autocorrelations for ARMA models are generally going to have regularity assumptions. That's not surprising, since that's what happens with them. Because I mean, think of this. I mean, if you think of AR models, then they have this geometric decay basically that you're going to show as well in the practical. In the example sheet, and then the MA will give you something that sort of has a hill, a cliff. So you sort of stop the correlation after Q lags, and with finite samples, you will never see that cliff exactly. So you will always have non-zero correlations. And if you try to combine both, then basically what you get is, some sort of combination, which is not very intuitive how to combine them together, but you do get some regularity. And so what is happening here is that we're seeing precisely something of that kind, right? So we're seeing some geometric decay. It's not really decaying so drastically, really. But what this fluctuation from negative to positive to negative means is that one of the parameters is going to be negative for sure. So I forget what the parameters were. But yeah, so the negativity will make it fluctuate. So just take a, let me just remember. So take an AR model, AR1 model with negative. Okay, so it's actually here, I think. Now that I remember, let's see. Okay, so if you plot in this one, just plot it for -0.9 rather than 0.9.
Yeah.
Then you will see that you get a very similar behavior, basically.
I mean, that kind of oscillates every period, doesn't it? Yeah.
Yes, exactly. So that will be positive, negative, positive, negative. Yeah.
I'll share this with people. It's just looking at that kind of oscillation made me think of some sort of product of an exponential decay with a sinusoid, which seemed like a lot like the stuff from like 1A ODEs when we're kind of solving second order differential equations and indeed second order difference equations. And that seems to be kind of exactly what we're doing.
Yeah. I mean, this has flavors of that. Yes. And I mean, after all, the time series is it has this this view that it would correspond to a discretization of some sort of stochastic process, and stochastic processes have a one-to-one correspondence with differential equations via expectations. And yeah, I mean, these things are related. Yes. Yeah.
Okay, that nice warm fuzzy feeling now. Okay, great.
No problem.
I'll hold off for a few seconds to let other people get a word in. But I've got a kind of general intuition question.
Okay.
I get a question about the computation of the ACF.
Yeah.
Why does the lag stop at 20? Because I think we should have enough data to compute at 50. Is it just the R function that stops because we're not interested?
Yeah. I mean, it's just because, you just stop at, I mean, it's a completely arbitrary choice. Yes. And I mean, you certainly don't want to go up to as many lags as you can compute, because, so I think that is somewhere here. So when I when I included this bit of theory, I said that this convergence will occur for lags going up to some capital H less or equal than n-1, and you're saying to go all the way up to n-1 because you can compute the quantity here. But the problem is that then if you go up to n-1, you will only have one data point to estimate something, and so that will be a terrible estimate, and so will be any that are close to the n-1, because we don't really have asymptotics in practice, and so it's better to truncate earlier than that if you want to have something realistic, right?
Yeah, okay, but that's the number of lag we compute change depending on the number of data we have.
Yeah, so you could have something of that kind, yes. You could try to say, well, I wish to have a certain precision, average precision, and then this precision will depend on the number of data points if you fix the H, and then you say, well, and therefore I can move this capital H, if you fix precision, then yes, this capital H will depend on the number of data points. And so if the number of data points grows, then of course you can have more and more of these for a fixed precision, yes.
I've just checked out the RDocs, and apparently there's an argument lag max, which you can add into the ACF function.
Yeah. I mean, but it's still arbitrary how many,
yeah.
Right?
But it scales about with log n.
Right. Okay. I mean, that's a bit slowly, but you could probably do a bit better than that. If you fix precision, then you would probably have asymptotics that are polynomial in n, but just
This is almost for convenience. You don't want to be going out to like 1,000.
Exactly. It won't really give you much more info than, generally speaking. I mean, these are diagnostic plots, right? So if you need to go to lag 1,000 to get an idea, then probably you won't get an idea, because the model will be so complicated. I mean, it's already difficult seeing this ARMA plot here. It's already difficult to try to guess what's going on with the parameters, right? So So having 1,000 lags won't really give you much more info.
Yeah, okay, I see.
Yeah.
In general, how do you detect signs of non-stationarity? We had 2 examples in this practical, but I wondered what general signs there might be.
Did we have 2 or? Oh yeah, we have the ARIMA and the. I mean, so I think in this one there is, it's. I think in this one is pretty clear, right? What's going on? As in, there is a clear change here in the variability. And so because of Hugh's question, then, we know that it cannot be stationary if you're changing the variances, right? And so that's the kind of thing that you would be looking for. And in many occasions, you will be able to pick that up easily from here. So, I mean, this is way too regular to be stationary. This region here. Let's see. I mean, okay. So just to start with, just compute the autocovariance or the autocorrelation function. Yeah, and that will give you pretty. So this is the autocorrelation function of this ARIMA process.
Yeah.
So that to start with, I mean, you just find this is not, this is not a very reasonable autocorrelation function to start with.
Yeah.
And so that should indicate that there is too much dependency well, not too much dependency, but that there is something here to be explored, at least. And, to me, this doesn't look like stationary, because this switch of regime, in some sense, is very suspicious, right? So, it seems that there is here a need to go down and then a need to go up. And even though, of course, it could be that you get such things by chance, it should be a warning, at least. And in general, I think in general, you should assume that things are not stationary.
Right.
And so it's a matter of, how do I transform this so that I get something that is sort of stationary?
I see.
So that I can analyze it with a model.
So to summarize, it would be changes in variance, so suddenly moving a bit more, and sort of like large scale movements and too much regularity.
Yeah, so you have trends, seasons. Those two things you certainly should be looking out for, because these are just, naturally they occur. And then once you remove those, you're left with the time series that shouldn't have any of those kind of characteristics. And so you'll be looking for, changes in the variance, sort of very apparent changes in the variance, or trends like this that cannot be, sort of piecewise trends, so to say. Those are the two things, right? Because after all, stationarity is the first two moments.
Got it. That makes a lot more sense now. And I just had one more quick thing to fit in before Lenny's question. With white noise, we define it to be uncorrelated, which is not as strong as independent. And in the practical, we've actually used Gaussian white noise, which is independent anyway. So I wondered whether you would ever use non-Gaussian white noise to generate these.
No one stops you from doing it. And I know that some people in the department would have introduced ARMA models directly with the Gaussian noise. So I think when it comes down to inference, so when it comes down to statistics, then people assume that you have Gaussianity. Because after all, you need to write the likelihood, right? If you want to do likelihood based inference, then you need to write down the likelihood, and then assuming Gaussian just makes your life so much easier. And in many occasions, it's not a bad approximation either. But if you come from a bit more of the time series stochastic processes world, which is a bit more my case, then the traditional definitions just assume a white noise. And so for inference, that means that you will at first not have likelihood-based inferential procedures. And there are ways of getting around that, basically. But it turns out that they're not necessarily superior to the likelihood-based ones with Gaussian assumptions. So it's a bit of a matter of style. I just wanted to introduce the usual sort of time series definition rather than statistics, modern statistics definition.
Got it. Thank you very much.
Let me just add to that something. And is that I'm gonna step on my own words now a bit, because the crisis of 2008, what it showed is that this assumption of Gaussianity actually was not the right one to consider, because there were unexpected shocks that cannot be modeled by the thin tails of Gaussian random variables. And instead, one should be using random variables that may not even have a second moment. So I'm talking about stable processes, for instance, which are a generalization of the Gaussian Gaussian, well, stable distribution is a generalization of a Gaussian distribution, and you can also have stable processes. And we just have 2 lectures for this course for time series, but I would definitely keep that question in mind if you're considering going into more financey world and so on. That the Gaussian assumption may be questioned, and you're very right in questioning it, basically, because it was questioned and models had to be changed to account for that.
Thank you.
Yeah.
If there is still some time, I just had a quick question.
Yeah.
At the end of the second part of the practical, of the first part, sorry, of the practical, where we define the function AMA to MA.
Yeah.
Just above this, it is said that an AMA process is causal if it can be written as an MA process with infinite order, etc. I would have thought that it would have been causal if it could be written as an AR process with the same conditions. Could you maybe give a little bit of explanation as to why, from the definition of the course, we can say that it is causal if we can write it as an MA process?
What did I give? I must have given. Yes, I gave. So definition 23. I said that an AR model is causal if it is linear with all of the negative index coefficients being 0. And that means exactly being MA with L1 norm of the MA coefficients being finite, right? It's equivalent. So.
Okay, yes. Sorry, that was just a misunderstanding from my part. Sorry.
Okay. No, that's okay. But I think you've got a point in that. And I think it's good to clarify this, because I think probably what you're thinking is, if it depends on the past, then surely it should depend on the past values of the time series. And what happens with these models, especially with AR and with AMA models, is that they are defined via this white noise. And so really all the information is contained in the first value and the white noise. But if they are defined on the integers, then there is no first value. And so they're really just defined via the white noise. And this is why we can write them as a linear, or why causality means writing it in terms of the present or past values of the white noise only, because it contains all of the information of a process.
Yes, thank you. It makes more intuitive sense as well now.
Yeah, sure, no problem. Lenny, do you want to ask? Because today I do have to run off.
Yeah, I mean, this can probably kind of wait to the office hour, but it's just like generally, I don't feel like I've got a great grip on what stationarity means, and I'd be quite like to explore that a bit more. In particular, maybe to start with that time series Y, which is on your display. You said like that doesn't look, the lag profile doesn't look very stationary.
Well, I said that there is certainly, I mean, it doesn't look, okay, I don't know exactly what I said, but I think I said this means that you probably wish to explore more than the autocorrelation function. And this is because it doesn't match the usual AMA autocorrelation functions. And so if you don't match the AMA ones being the absolute baseline of stationarity, then that's why you maybe question stationarity there. And that was my reasoning. And stationarity in general is a preservation of first and second moments across time shifts as well.
Yeah.
So I mean, that is what it is. I mean, it's just that you expect your first and second moments to to be invariant to time shifts when you look at your time series. So that's pretty much that's it.
Yeah.
There's no more.
So
That.
why isn't a random walk stationary? Because it feels to me that like,
I mean,
it feels like your second moment should be invariant to time shifts.
no. So if you take the variance there,
Yeah.
it's not. I mean, think of a random walk as a discretization of Brownian motion. Brownian motion doesn't have. It doesn't have the variance to be stationary.
The variance always increases.
Yeah, exactly. Yeah.
Which is, yeah. And so, oh gosh, it is late. Yeah. I guess again, in that nice flattened curve we have of the ARIMA process. So what we're concerned about is like not the fact that it's kind of got this big trend, because we could get a trend like this if we just had kind of a really regularized arm process, which would be kind of looking very, very close to some sort of Brownian motion, would be kind of continuous. It's like what we care about is the fact that there aren't the small fluctuations. Is that some sort of intuition, or?
I mean, I was thinking a bit less than that. So I was, because it's dangerous to try to read too much info from it, and that I think you're on the verge of that basically now, by that reasoning you're giving. I mean, what this means, of course, is that there is a lot of. What this means is that there is a lot of correlation between adjacent data points, and also, with two lag adjacent data points and so on for many lags. So of course that means that there is, the path is very smooth. So I wouldn't say this looks like a Brownian motion. Brownian motion.
Yeah, no, it yeah.
Yeah, I mean, Brownian motion is just, it wouldn't have a profile like this. So that amount of smoothness, is something that means that it's very hard to maintain the same mean and the same variance if you're depending so much on all of the previous values, right? That would be the very first thought that would cross my mind, basically.
Okay.
Right.
Yeah. It feels like you should be able to even like make a strictly stationary process, which is smooth.
Yeah, so I mean, I'm not saying, so this is a diagnostic plot. It doesn't tell us all of the story. Yes, absolutely. Yeah.
Okay, thank you.
Okay.
I'm still developing intuition, but I think that really helps.
Sure. That's okay. Okay, so if you have any more questions, I do have to run off. If you have a very, very short one, otherwise we'll stop it here and you can come to the office hour or ask in the next practical or on Wednesday as well next week.